From here on, I'm going to present the most common geophysical techniques by showing an image of the acquisition, describing what the data is, and giving an example of interpretation. So I'm going to start with electrical resistivity tomography, or ERT, which is the ability of the subsurface to resist a DC electrical current. These values are then used to create a section of resistivity which can be interpreted for ground conduit. Here, a ERT line has been acquired next to a spillway which is thought to be leaking. In the interpretation of the data, what we see is that the engineered bank, which is represented by these red zones representing dry granular material, is punctuated by two zones of decreased resistivity, which are thought to be where significant moisture ingress has occurred. There's also a shallow zone of decreased resistivity, which is where water is ponding in the shallow subsurface. Ground conductivity surveys measure the conductivity of the top 2 to 4 meters of the subsurface as the instrument is walked in parallel lines over the area of interest. Higher values suggest increase in clay and moisture content. In this example, localized zones of high conductivity values suggesting moisture are identified in the granular material of the battered sides of this overflow channel here. Magnetic surveys indicate the presence of ferrous material within the subsurface as the instrument is walked over the area of interest in the same way as a ground conductivity survey. Pipes and reinforced concrete slabs often comprise ferrous materials, making them detectable in such surveys. In this example, we have found a pipe that extends from the valve tower to a large manhole cover at the edge of site. Over here, we find a lineation of significant ferrous structures which are likely to relate to either pipe or pipe infrastructure during the construction phase. GPR surveys use the emission and detection of radio waves to ascertain the structure beneath the spillway or within the dam core. Data can be used to observe anomalous features such as shallow voiding as a result of fines washout beneath masonry. So the GPR is pushed over the area of interest. It can also be rigged up to be pulled up near vertical structures, and I have a photo of this at the end. This example shows a zone of washout as high amplitude response beneath a non-reinforced concrete slab, the base of which is highlighted by this red line. Seismic surveys involve the generation of an elastic wave at a specified point, usually by a sledgehammer, as shown in this image. The resulting types of seismic waves are then measured and interpreted. The P waves can be used to find the thickness of layers exhibiting different seismic velocities. These can include engineered layers, overburdened deposits, and the presence of weathered and competent bedrock. The S waves can be used to divide the subsurface into layers of different strengths. This can indicate the depth of uncompacted and compacted sediments, weathered rockhead, and more competent bedrock. Surface waves can then derive the stiffness of ground material. TEWDAT have shown repeatedly that the careful use of ERT, ground conductivity, GPR, magnetics and seismics all provide important information on dam structures and reservoirs. Now I want to provide some information on the use of time-lapse geophysical surveys, as there's increasing demand to observe defects over time and how they respond to changing water levels. By repeating exactly the same ERT lines, we can provide information on the evolution of moisture content in an embankment. The temporal resolution of this data can be specified by the client from daily or twice a day to only once a year. Here are some examples of leak evolution observed in ERT data. In these first two examples, the baseline ERT, i.e. prior to a leak when the water level was relatively low, show the character of the embankment. Once the water level is raised, we find that there's isolated zones of decreased resistivity, which is what would be observed if water was infiltrating a relatively clay-rich material. And from this, we can see where leaks would likely spring out in the dam face or the embankment. In this third example, the baseline survey has identified this zone of granular material. Once the water level it has been raised and a leak has started, what we find is this area becomes more resistive, which is the opposite to what we would expect. And this is because in this environment, it's incredibly clay rich and fresh water is within the reservoir. So an increase in resistivity has occurred. And this just goes to show that ERT can be very useful in measuring different types of leaks in different types of water, but you have to be careful in the interpretation of the data. Self-potential methods in geophysics are well established but not often used. Self-potential measuring for leak detection works in this way. So we take a series of measurement electrodes where we think there is a leak or where there's a chance of a leak, and we measure the voltage between those and a reference electrode which is away from the leak in a quiet area of the embankment or even further away than that. As water flows beneath the measurement electrode, they cause a voltage due to the drag between the mineral grains and the water flow, which is a measurable value. Teradat have been involved in creating a monitoring system using this method and this technique. It's called SpyVolt, and we have successfully measured leaks in several locations with this technology. However, it is still in the beta testing phase. We have written up this work in the March edition of the Ground Engineering magazine, where more details can be found on this specific case study. But I will briefly show you the results here. And what we found is that when we acquired both ERT surveys every sort of 4 to 5 weeks and related that to our SP survey, which was taking measurements every half an hour for over 3 months, what we found is that as the water level interacted with this zone of granular material, our leak began and then broadened out as the water level interacted with this zone of granular material. And at the last point, it created a very broad leak within the dam face, which corresponded almost exactly with this granular material here, which was a very positive result. And we're hoping to use this technique more widely. And as I say, it's still in the testing phase, but we're quite confident that this will be a useful thing for the water industry in the future. Here are some fieldwork photos from our recent works on dams and reservoirs. Thank you for taking the time to listen to our presentation. I'm happy to take questions now, or if something comes to you later, please get in touch over my email. My email address is just joe@teradat.co.uk, or just call Teradat and we can help you out. Thanks again.